For decades, the default method for managing the world's organic refuse was simple: bury it. Millions of tons of combustible and biological material were driven out of cities and compacted into massive, sprawling landfills. In 1999, the European Union implemented the Landfill Directive, strictly banning the dumping of organic waste. The goal was to reclaim land and eliminate the slow release of methane gas into the atmosphere. That refuse had to go somewhere. Instead of rotting in the ground, organic material is now systematically harvested and routed into specialized plants to generate district heating and electricity. These facilities form the backbone of a biogeneration grid designed to replace the baseload power historically provided by oil-fired plants. But removing fossil fuels from the equation introduced a hazardous variable. By consolidating unprecedented volumes of reactive organic material, we have engineered a localized, highly unpredictable industrial fire hazard. International environmental policy has outpaced safety frameworks, leaving dangerous blind spots in the energy supply chain. The root of this hazard lies in energy density. Liquid fossil fuels pack an enormous amount of combustible energy into a small footprint. Solid biomass yields significantly less energy per kilogram. To achieve the exact same gigawatt output, grid operators must scale up the physical volume of their fuel supply by orders of magnitude. That mass is further expanded by the material's low bulk density. Solid fuels like wood chips and pellets do not sit flush. The air gaps between the fragments stretch the total storage footprint even further. To maintain necessary winter reserves, power facilities must construct massive indoor warehousing and sprawling outdoor stacks, packing bales of sorted refuse and wood pellets floor to ceiling. While oil is stored in engineered, sealed tanks, these bioreserves are exposed, porous, and constantly interacting with ambient air. This exponential increase in the physical volume of biological material creates the exact geometric and chemical conditions required for systemic thermal failure. We can track the velocity of this transition using historical records from the Swedish Energy Agency, which map the national scale-up of bioenergy dependence. Between 1980 and 2006, baseline bioenergy use across Sweden expanded by 142% as industries and municipalities aggressively shifted away from heating oil. This table details the projected gross bioenergy supply required to hit future climate targets. In 2005, the total supply sat at 108 terawatt-hours. By 2020, that requirement leaps to 154 terawatt-hours. The 2050 projection reaches 228 terawatt-hours, doubling the raw material entering the supply chain. Processing this load requires packing these massive fuel stacks closer together. To minimize transport costs, these reserves are increasingly positioned directly adjacent to the power plants and urban centers they serve. The modern grid's survival relies on a physical supply chain so large it mathematically guarantees a rise in industrial accidents. The danger stems from a core chemical distinction. Unlike inert reserves of crude oil, organic waste and wood chips are biologically active. A moist pile initiates a two-stage thermal runaway. It begins with microbial activity. Microscopic bacteria and fungi begin to rapidly digest the organic fibers, and their metabolic processes generate a tremendous amount of heat deep inside the stack. The massive volume of the pile acts as a thermal blanket. The heat generated by the microbes cannot dissipate. It becomes trapped in the core, slowly driving the internal temperature upward. The microbes eventually die off, pushing the core temperature past a critical threshold. At this specific temperature, physical chemistry takes over. This is chemical oxidation, where the material begins reacting directly with the trapped oxygen. The reaction accelerates. The slow microbial heating transitions into an intense thermal zone, consuming oxygen and generating extreme heat. Without any external spark or human error, the core reaches its ignition point, and the pile sets itself on fire from the inside out. An industrial biomass pile is an unmanaged, slow-motion biological reactor. To prevent catastrophic ignition, traditional energy sectors rely on exact metrics to manage their storage reserves. The petrochemical industry relies on mathematically defined risk parameters. Engineers know the exact flashpoint and explosive limits of every liquid they store. But those universal parameters do not exist for solid biofuels. The metrics for organic material are completely undefined. Every batch of refuse has a different moisture content, density, and chemical composition. There is no standardized formula to predict its behavior. This leaves facility operators working in the dark. Without a defined baseline, engineers cannot distinguish between a normal microbial temperature rise and the dangerous onset of chemical oxidation. Standard industrial fire codes and traditional early warning detection systems were built for oil and gas. When applied to deep-seated biological heating, they are largely useless. The modern energy grid operates massive organic reserves blindly, lacking the mathematical boundaries required to ensure safety. When auto-ignition is achieved inside a tightly packed waste stack or an enclosed storage silo, the crisis is immediate. Traditional firefighting tactics often fail. The fire is deeply seated in the core, insulated by hundreds of tons of material that physically repels standard water suppression. As the organic matter burns in an oxygen-starved environment, it releases massive volumes of thick smoke and toxic gas, blanketing the surrounding area. The suppression effort creates a secondary hazard. The millions of gallons of water required to battle the blaze mix with chemical ash, creating polluted runoff that threatens local groundwater. Beyond the physical damage, the grid suffers a systemic blow. The facility loses its winter energy reserves, and the heat often forces the shutdown of adjacent power infrastructure. The resulting loss of fuel, damage to heat distribution, and massive toxic emissions can erase the environmental and economic benefits gained over several months of operation. Securing the energy transition depends on precise industrial safety frameworks to support the new scale of the grid. To address this, organizations like MSB and SP has proposed research programs to map the industrial fire science of biomass storage. The first priority is quantifying exact risk parameters to categorize the volatility of solid waste and biofuels. This enables advanced sensors to track invisible chemical precursors, catching oxidation long before ignition. Finally, industry must develop specialized suppression tactics to penetrate and cool deep-seated fires. To break our reliance on fossil fuels, we must master the volatile, unpredictable physics of the organic world we are using to replace them.